Okay, so we're delighted to have Maya Verma from the University of Oklahoma, who's going to be talking about Leighton's property of XMN.
Thank you, Alex. Good afternoon, and thank you for inviting me to give a talk here. So today I'm going to talk about the Leighton's property in the Baumslag-Solitar complex, which I'm going to denote by XMN. So in 1982, Leighton proved that any two finite graphs share a common finite cover if and only if they have the same degree of refinement. That is, if they have the common universal cover. Right? And here is an example of graphs A1 and A2. Both of them are 4 regular, hence they have the same universal cover, which is the 4 regular infinite tree. Therefore, by the Leighton's graph theorem, these two graph admits a common finite cover. Now, one can ask to which kind of spaces we can generalize this Leighton's graph theorem. And here are, so first I'll define what is Leighton's property for me. So I'll say that a space X satisfies Leighton's property if any two compact spaces whose universal cover is X share a common finite sheeted cover. And what are some example of spaces which satisfy Leighton's property? So the first one is tree. Tree satisfy Leighton's property because we have the Leighton's graph theorem. And spaces which looks like this. These are tree of spaces with vertex spaces regular polygon and edge spaces point. So these satisfy Leighton's property by the result of Sam Shepard, Daniel Woodhouse, and Giles Carden. In 2006, Hugland conjectured that special Ket-0 cube complexes also satisfy Leighton's property. And in 2022, Woodhouse proved this conjecture for a small family of Ket-0 cube complexes. These are NPC cube complexes, which exhibit symmetry and homogeneity similar to regular graphs. And our last example is the Baumslag-Solitar complex for certain M and N, XMN for certain M and N, and I'll tell you which one. Okay, so let's see how this Baumslag-Solitar complex looks like. So a Baumslag-Solitar group is a group with the following presentation. It has two generators, X and T, and one relation, T inverse X to the power N, T is X to the power M. And the cell complex here is the presentation 2 complex for the Baumslag-Solitar group BS25. So it has one vertex, that is all these vertices are identified, two edges labeled T and X. So the two vertical edges are identified and the horizontal edges are identified. And there is one 2 cell which is glued along the relation T inverse X square T X to the power minus 5. Now, XMN is actually the universal cover of the presentation 2 complex corresponding to BSMN with the induced cell structure. So XMN will have a lot of lines which are lift of these horizontal edges and strips which are lift of this 2 cell. And here is a local picture of how X52 looks like. So it is made up of, it has a tree-like structure. It is made up of these lines, horizontal lines, and a lot of strips. And for each horizontal line, there are 5 outgoing strips attached to it and 2 incoming strips attached to it. And this is the main and only theorem of my talk. So I can write each pair of integer as dm comma dn, where m and n are co-prime. For example, I can write this 610 as 2 times 3 comma 2 times 5, and now 3 and 5 has GCD1. Or for 515, I can write this as 5 times 1 comma 5 times 3, and now 1 and 3 has GCD1. Right? And the theorem states that if m and n are co-prime, then x dm comma dn satisfy Leighton's property if and only if m and n has no divisor less than or equal to d, which is equivalent to saying that GCD of m and n with all the integers less than or equal to d is 1. Now the proof of this theorem for the case d is equal to 1 follows from the work of Baumslag-Solitar and Forrester. Now for the rest of the talk, I'll give the idea of the proof, and I'll need a few tools for that. So first of all, I'm interested in finding compact spaces which are covered by these giant tree-like cell complexes. So if something is covered by the cell complex, then how will it look like? So each horizontal line will cover a circle, and each strip will cover an annulus. So the quotient space will look something like this. So it is a space made up of some circles, some annuli, and gluing map from boundary of some annuli to some circles. Right? And this is a fiber 2 complex. And I can associate a labeled graph to this fiber 2 complex. Right? So to associate this label graph, I'll put a vertex for each circle and an edge for each annulus. So I'll get this graph, and these labels on the edge tells me how to glue the boundary of the corresponding annulus to the circle on the vertex. So this label graph looks much simpler than the fiber 2 complex, yet it uniquely defined the fiber 2 complex. So it's easier to work with this label graph. And now I'm also interested in finding covers, finite sheeted cover of these fiber 2 complexes. So it turns out that finite sheeted cover of fiber 2 complex is again a fiber 2 complex. And there is one-to-one correspondence between the covering space of fiber 2 complex and something called admissible branch cover of the corresponding label graph. So here is an example of a fiber 2 complex. It is made up of 2 circles and 1 annulus. And this is a 4-degree cover of this fiber 2 complex. So this circle cover this with degree 4. These 2 circle cover this with degree 2, and these 2 annulus cover this with degree 2. And I can encode this covering map into admissible branch cover of this label graph. So what is an admissible branch cover of a label graph? It's again a label graph with a surjective graph homomorphism from the graph upstairs to the graph downstairs, and a degree function from the set of vertices and set of edges on the graph upstairs to natural number. Right? And these degree function, and this degree function, which are these green numbers actually, it defines what it uniquely defines what is the degree of these maps, right? From circle to circle or annulus to annulus. So we have admissible branch cover. And now the idea of the main theorem, or the proof of the main theorem. So if a compact space X is covered by X dm comma dn, then we just discussed that X will be a fiber 2 complex, and we can associate a label graph to that fiber 2 complex. Now, it turns out that these label graphs satisfy some conditions, which I am hiding in the star. And these condition records the fiber 2 complex structure of X as well as the covering map. And also if I have a label graph which satisfy these conditions, then it will be covered by XDN, DN. So it is an if and only if statement, and this is a result of Forrester's paper in 2022. So I'll prove the reverse direction first. So by this result of Forrester, now the task of finding finite shaded cover of fiber 2 complex reduces to the task of finding admissible branch cover of label graph. And to prove the reverse implication of this theorem, I'll start with a label graph satisfying the conditions hidden in the star. And I will build a 2D regular cover, admissible branch cover for that label graph. So this is just an example, and we can generalize this example. So this is an example of a label graph in X610. So the fiber 2 complex corresponding to this label graph is covered by X610. And so for 610, the color for 610, I can write 610 as 2 times 3, 2 times 5. So D is 2, 3, M is 3, and N is 5. So first I'll fix a prime number which is less than and equal to D. Here D is 2, so the only prime less than 2 is 2. So I'll fix the prime number 2. And I'll fix a vertex in my graph, any vertex. Here I'm fixing this vertex at the bottom. Now I'll look at the label near that vertex. If any of the label is multiple of P, I'll divide my graph at this vertex into P pieces. Right? So here, if the label is even, I will divide my graph into 2 pieces. So both 6 and 10 are even numbers. So I'll divide my graph into 2 pieces, first piece, second piece. I'll move forward. On the second vertex, this label is even. So I'll divide this subgraph into 2 pieces, here, here, and then for the second piece again, 2 pieces. And I'll do the same thing for this vertex and this vertex. For this vertex, there are no even labels, so I won't do anything on this last vertex. And by this process, I will get this colorful graph at the end, which is actually an admissible branch cover for the graph that I started with. And these green numbers are the degree function of this admissible branch cover. Now, in general, I can do this for any prime P less than and equal to D. And this construction works because P does not interact with M and N, or the GCD of P, or P does not divide M or N. Now, if we look at this admissible branch cover, it is 4 regular. Each vertex has valence 4. And each vertex looks the same. That is, for each vertex, you will see 2 edges with label 5 and 2 edges with label 3. So the graph, each vertex of this graph looks the same. Now what I'll do, I'll take any 2 label graph whose fiber 2 complex is covered by this X610. By this previous construction, I can build 4 regular cover of these graphs. And now I have the Leighton's graph theorem, which says that if your graph are same, or if they have the same universal cover, then they admits a common finite shaded topological cover. So for these two graphs, I can get a common topological cover, and I can also define the labeling, or these topological covers are actually admissible branch cover as well, or every topological cover of a graph is also an admissible branch cover. So I have admissible branch cover, composition of admissible branch cover is again an admissible branch cover. So I started with two label graph and I built a common admissible branch cover. This is what I wanted for the reverse implication of the theorem. So this is the end of first implication. Now to prove the forward implication, I will do the contrapositive of the theorem. That is, I'll prove that if M or N, if GCD of M or N with I is not 1 for some I less than or equal to D, then X dm comma Dn does not satisfy Leighton's property. Okay, and to prove this direction, what I'll do, I'll build fiber 2 complexes covered by X dm comma Dn, whose fundamental groups are not commensurable. This will imply that the fiber 2 complex does not have a common finite shaded cover. So let's assume that either GCD of M or I is not equal to 1, or N or I is not equal to 1 for some I which is less than or equal to D. So there are two cases, either D is I or it's not I. If I is equal to D, then I'll further, but did I mess up somewhere? Okay, if GCD of M and D and N and D is 1, then I'll further split this into two cases. Either both M and N are strictly greater than 1, or one of them is 1. So I have these three separate cases, and I'll give example of fiber 2 complexes covered by XDM comma Dn in these three cases. And these example uses different techniques. So for the first case, when GCD of M and D or N and D is not equal to 1, then these two labeled graph defines fiber 2 complex which are covered, which is covered by X610, and these graph has inequivalent depth profile, which is a commensurability invariant. It was built by, again, Forrester in his paper in 2022. So these two graphs have different depth profile. That's why their fiber 2 complex has incommensurable fundamental group. Hence, the fiber 2 complex does not have a common finite shaded cover. The second case, so these are the label graph whose fiber 2 complex is covered by X515. Now, in these graphs, there are a lot of ones because, there are a lot of ones. So I can do deformation moves on these graphs, which is equivalent to, which is homotopy equivalent on the fiber 2 complex to get these bouquet of circle. Now, this bouquet of circle has three kind of loops. One loop with label 1 and 3, some loop with label 1, 1, and some loop with label 3, 3. And now I can count how many loops are there with label 1, 1, how many loops are there with label 3, 3. Similarly here. And this way I will get two vectors, 4, 4 and 1, 5. And these two vectors are linearly independent. That's why the label graph that I started with does not have a common admissible branch cover. And this construction of this vector is generalization of a vector which was introduced in this paper by Kazal-Struich, Zakhar, and Kazachkov. So the vector that they built was isomorphism invariant, and I generalized this to commensurability invariant on a bigger class. And the last case is when both m and n are greater than 1. So these are example of label graph whose fiber 2 complex is covered by X69. Now these graph does have no proper p-plateau, and the notion of p-plateau was introduced by Levitt, and it turns out that if the label graph does not have any p-plateau, then every admissible branch cover is actually topological cover. So if these two graph does not have common topological cover, then they does not have a common admissible branch cover as well. Right? And it turns out that these two graph will have a common topological cover if and only if they'll have the same number of vertices and same number of edges. Right? Now, although they have the same number of vertices, 2, the number of edges are different. One has 6 edges, other has 5 edges. So these two graph cannot have common admissible branch cover. And this is the end of forward direction. And this is also the end of the talk.
Okay,
Thank
thank
you.
you very much. Let's thank Maya.